session co-chair. And it is my great pleasure to introduce Professor Changyoung from Seoul National University, also from IBS Center for Correlated Electronic System. He is famous for his seminal contribution to understanding of correlated matter, especially using ARPES technique. And today, he's going to talk about searching for new electronic properties in ultra-thin films of correlated materials. Let's welcome him with a big hand.
Okay, thank you, Sharon. And I would like to thank the organizers for this opportunity to present my recent work at this beautiful place. So today I'm going to talk about our recent work on our recent in-situ ARPES work on thin films of correlated materials, especially in the ultra-thin limit, means only few unicells or few atomic layers. So here I show you the famous two-phase diagram on high-density superconductors and here correlated topological materials. And in this phase diagram, you see that there are many exciting novel phases here. And we all look for exciting phases where interesting physics lies. And of course, if we can add another dimension, that's a new knob we can turn and find different phases. And that's what we are hoping for. So, in fact, there were already many presentations regarding 2D Banderas materials with twisted layers. And you can exfoliate and stack and twist, and you can make Mott patterns, and you can find unconventional superconductivity and other very exciting phenomena. What you do here is that you actually change number of layers or charge carrier density or electric field, temperature, magnetic field, whatnot. So you basically turn different knobs to find new physics, new interesting physics. We can do that in a more conventional way. That's using thin film growth. But here, I'm going to talk about in the ultra-thin limit. So, you can, in thin film growth, you can change number of, you can vary film thickness. So you go from bulk 3D down all the way down to ideal 2D, that's a monolayer. So you can basically control dimension. You can also control strain or distortion from the substrate. You can also think about proximity effect from symmetry breaking in the substrate. For example, if you grow something on ferromagnetic substrate, you can have some proximity effect to the thin film. So we can artificially control the properties of this thin film. Of course, to look at this proximity effect, you need to work on very, very thin film, only a few layers, because that's not going to go too far from the interface. So that's basically ideal. And what I do is using this 2D thin film growth and combine it with the in-situ spectroscopy, that is ARPES, and study the electronic structures. Why do we have to do ARPES? If you think about this thin films of atomic layer, transport measurement is extremely difficult. I will show you later that one of the reasons is that if you were to measure, for example, electrical conductivity, there are stem edges, and these stem edges break thin film into pieces. So there is a connectivity measurements are actually quite difficult. And also, if you were thinking about magnetic susceptibility, the volume is so small. That also makes measurements very difficult. Here, I do in situ ARPES, and I can measure electron structure. And I will show you, we can also measure a spin. So we can also check out the magnetism. So again, we have a symmetry breaking substrate, and hopefully we can have a proximity effect to the thin film, and we can control properties of this ultra-thin films. So that's the idea. Gabor was here, so I was going to show you this view graph for him. In situ ARPES is not really new. Many people do that. As far as I understand, the first work was actually done by Dr. Kabuna, 2003, on LESCO thin film, and I think that was grown on LSAT. So there was a compressive strain, and the TC went up, and this foamy surface is different from the usual cuprate. So now this became electron pocket, and TC went up to 40 Kelvin. So that was one of the very early work. And of course, afterwards, about 10 years, studies on these oxide films came out from Cornell group using oxide and beam, and they are very interesting, fascinating works. However, these studies all look at fairly thick film, 50 layers or so. Now, let me show you what we did from here. So to do that, we have this cluster system for in situ ARPES. I have two ARPES systems, one equipped with a spin detector, and I have MB for chalcogenide samples, films, and PLD for oxide films. And also, we can make some surface systems using prep chamber that's equipped with sputter annealing system. So using this chamber, we grow films, oxide in PLD, MBE, and prep chamber, and we transfer films to ARPES chamber without exposing them to the air. So that's what we do here. We also have ultra-high resolution ARPES, and hopefully we can add time-resolved in situ time-resolved ARPES here, so we can do dynamic studies. But for now, I will be mostly talking about results from these two systems. Actual system looks like this. Oh, yeah, okay. All right. This was one, and exactly the mistake it predicted. Okay, so here's ARPES 1, 2, there's a spin detector, MBE behind this system, and PLD on this side. We transfer samples into ARPES chambers and measure ARPES. So here's an outline of my presentation. The first system we started with was strontium luthanate, and there are many interesting results came out of this system. We are currently working on strontium iridate, also single pop-oxygen plane cuprate, and some chalcogenide systems here. But due to the time limit, I will be probably covering 1 and 2. So strontium luthanate is oxide ferromagnetic metal. It has pseudo-cubic structure. It's a perovskite with octahedron distortions, and it's in ortholongate structure. It's a ferromagnet with a TC around 160 Kelvin. So if you measure magnetization as a function of temperature, it goes up. TC here. The resistivity mostly behaves like a foggy liquid, but at TC there's a kink because the spin magnetic fluctuation is suppressed below TC, so that suddenly becomes a formulated-like behavior. Meanwhile here, the resistivity is more or less linear. Ruthenium is in ruthenium 4+ configuration, so there are 4 electrons in T2G orbitals. So magnetic moment for ruthenium is around 2 or something, slightly smaller, due to mixture of local magnetism and internal magnetism. And it has moderate mu as well as moderate spin coupling. So we grew PLD, we grew thin films of strontium oxide in PLD, and 4-unit cell strontium ruthenate shows a very nice is a terrace. That means strontium ruthenate grows in something called the step flow growth mode. So it grows along terrace, and you can see that this terrace of the substrate can be seen very nicely with the steps, very nice steps. Reed pattern shows oscillation initially, but it flattens because it grows in step terrace mode. If we measure longitudinal resistivity as a function of temperature for thick films, this resistivity looks more like from bulk with a kink at high temperature and more or less a formulated-like behavior with a fairly high triple R ratio. But as we reduce the thickness down to 4 unit cell, that becomes at very low temperature, it shows insulating behavior. Now we measure magnetization for thick films. TC is slightly lower than bulk value, but at 4 unit cell, it's down to 110 or 120 Kelvin. If we grow less than 4 unit cell, 3 unit cell is sort of ferromagnet, but below that becomes paramagnetic. So now here is in situ ARPES. I think this was 4 unit cell that can be compared with in situ ARPES on strontium ruthenate thin film from Cornell, grown by oxide and B. As far as ARPES goes, the quality seems quite similar. So we know that we have a fairly good film here. Now, getting to interesting physics here. Let me first talk about these topological structures and tunable anomalous Hall effect in strontium ruthenate thin films. This was published in these 2 papers. So, anomalous Hall effect was found more than 100 years ago, as you know, and it's supposed to be roughly proportional to magnetization. And if you recall the magnetization as a function of temperature, it looks like this. And this doesn't change whether you look at films or bulk. However, it was reported that if you look at film and single crystal and some doped films, as a function of temperature, this anomalous Hall effect changes drastically, even changes sign from negative to positive. So why does it happen? Why is it not proportional to magnetization? The first suggestion came from Nagaoka group about 20 years ago. They proposed that there's a magnetic monopole at the gamma point in the momentum space. Then what can happen is that as you change temperature, this magnetic monopole moves up and down in the energy, and they can cross Fermi level. Then they can also change. Then you can change the sign. So that was a first proposal, and that attracted a lot of attention. Soon after, some sources came out. For example, in this work from University of Toronto, their calculation shows that these monopoles are not at the gamma point, but at different. Actually, there are many monopoles in here. Also, very recent work in recent calculation for thin film show that there are 4 singular points where Berry curvature is very strong, where there are Berry curvature sources. So why is there such a difference? One problem in this business was that there's no experimental ARPES data on strontium loosenate, and that's because there was no suitable single crystal. So one possibility is that, of course, we can now grow high quality thin films that can be considered as single crystals. So we can do ARPES on these films and see where these Berry curvature sources are. So that was the idea. Now let's look at some data. Here I show you anomalous Hall effect data as a function of film thickness, so 4 unit cell, 5 unit cell, 6 unit cell, 7 unit cell, and also as a function of temperature. So this is low temperature data, that's high temperature data. You see that anomalous Hall sign here, but also we have this some Hove structure here on top of this anomalous Hall effect, and we believe that's due to topological Hall effect, and we reported this in these 2 papers. But this topological Hall effect in ultra-thin films is a little controversial, so I'm not going to cover this one. What's less obvious in this plot is actually sign changing anomalous Hall effect. If you look at thicker films of 7 unit cells, you see that you start from upper left corner to lower right corner. But in this very thin film, you start from lower left corner to upper right corner. So you see that this anomalous Hall sign is different between these 2. If you look at this 5 unit cell data, you start with minus sign, but as you increase the temperature somewhere, it actually changes sign here. So even within a single system, the temperature also, as a function of temperature, the sign of anomalous Hall effect also changes. So this is very peculiar, and that's what was reported, similar to what was reported earlier. So here we perform spin ARPES data first. Above TC, we don't see any spin polarization, but below TC, we see spin polarization at different parts of the brilliant zone. And to do that, we magnetize film in the in situ also. Now, we can also measure Fermi surface map, as shown here. In situ, measure Fermi surface map, and we can use a time binding model to fit the experimental dispersion using this model here. By analyzing this 2D time binding fit of the data, we can find topological properties of these bands. So let me slowly show you what we found. So here I show you a very generic Fermi surface of 2-dimensional Fermi surface of perovskite materials. These perovskite materials, T2G from T2G orbitals. So here is a beta band, here is a gamma band, and here is something called the alpha band. And that one, beta and alpha, has dxy and yz, dyz and zx characters, while this gamma band has a dxy band, character. Now, because this goes through ferromagnetic transition, each band splits into majority and minority bands, and that has this one with a bit of spin-off coupling, they hybridize. Now, it turns out to be that only few of these bands matter, because band curvature sources only near Fermi level is important. So here are Fermi surfaces that are important. So if I cut through one direction here, then the band structure looks like this without spin-off coupling. Now here we have dxy minority spin and yzx majority spin. With the spin-off coupling, they hybridize and opens up a gap, and they become very curvature sources. So we can notice two. One here between gamma and beta and gamma band crossing here. So let's call that number one. And number two is hybridization between YZ and ZX. And this number one is shown here. This guy is a nodal line because it's a very curvature. Nodal line is the very curvature here. And also this quadratic band crossing opens up a gap due to spin-off coupling and has very curvature sources as shown here. So you can, based on this time binding fit, you can calculate very curvature. And what's shown here is a calculated very curvature from the time binding band. And here is a brilliant zone, and very curvature mostly comes from these four corners of the brilliant zone. And it turns out to be that most of the very curvature actually comes from this quadratic band crossing. So how this helps to understand this sign-tunable anomalous Hall effect. So let me show you what happens. So here is this quadratic band crossing, and here's a majority band, and that's a minority band, and they are split by exchange interaction. And also there's a Fermi level, and as you change splitting or change the position of Fermi level, that affects this whole conductivity, anomalous Hall conductivity. So as a function of n, as symmetrically shown here, it changes the sign. Also as a function of Fermi level, up and down, it changes anomalous Hall conductivity drastically. That means we can actually control anomalous Hall conductivity by moving Fermi level up and down. That's what we did exactly. Using ionic gating on this 4-unit strontium lutherate and 5-unit you can, as we change the gating voltage here, we can change anomalous Hall effect. In this case, you can tune it from negative all the way down to 0. We need it higher voltage to change, convert it to positive sign, so we couldn't get there. But anyway, we were able to control anomalous Hall effect. So that was a 4-unit cell film. Now, we wanted to go all the way down to 1-unit cell of strontium lutherate, and let's see what we can do here. So there was a issue whether this 1-unit cell is a metal or insulator. This actually dates back to 70s, where whether these two-dimensional systems are susceptible to Anderson localization and inherently become insulators. Same issue was here, whether one unit cell is a metal or insulator, and there were actually recent conflicting reports. One says it should be a metal, and the other one reports it's an insulator. Here, also in situ ARPES can play a role in resolving this issue. Initially we tried very thin film, only 2 units there, but we couldn't get proper data, and it turns out to be that there was a charging problem in photoemission process. What happens is that in photoemission we shoot photon and kicks out electrons here. So these electrons or the charge should be compensated from outside. However, this 2 unit cell, because the stem edges, they are broken pieces. So supplying these electrons is not possible in these ultra-thin films. So we devised a heterostructure system as shown here. So we have STO substrate as usual. We grow 4 unit cell of strontium leucine that provides electrons. And here's a STO 10 unit cell and grow N unit cell of SRO. So using ARPES, because that's a surface sensitive, we only look at this surface top strontium leucine layer. However, this 10 unit cell STO is thin enough so that electrons, the current leaks through this 10 unit cell of STO to this top strontium leucine layer. So we don't suffer from this charging problem. Here I show you a TN picture of this structure. We have STO, 4 unit cell of SRO, and 10 unit cell of STO, and 1 unit cell of SRO. So we can grow a fairly nice 1 unit cell SRO on top of this structure. Now, we took ARPES data, photoemission data as a function of top SRO film thickness, roughly here. Now let's focus on to this near Fermi level structures. Without strontium leucine layer, I'm looking at 10 unit cell STO. So it's nothing because STO is an insulator. I have no spectral weight. Now I grow 1 unit cell, and I see some structure here, 2 unit cell, 3 unit cell, and 4 unit cell. I have very nice Fermi edge here. Now let's look at this thickness dependence. And 1 unit cell, so as we reduce the film thickness, this Fermi step, Fermi edge becomes smaller and smaller. And 1 unit cell, it's almost 0, but we still have finite edge here. It's small, but very clear Fermi edge for 1 unit cell strontium leucine film. And also another thing to notice is that you have this hump at around 1.5 eV binding energy, and that's more luminescent of low Hubble band. So as we lower the film thickness, we suppress some spectral weight or Fermi edge, but not down to 0. We still have some Fermi edge here. Meanwhile, also this low Hubble band like feature grows. So first of all, this is really first observation of clear Fermi surface of 1 unit cell SRO film. 4 unit cell Fermi surfaces are very clear. 1 unit cell, even though we still have this spectral weight. that means one unit cell is still metallic in terms of spectroscopy. So let's look at this field thickness dependence. Here I'm plotting 1, 2, 3, 4, 5 unit cell Fermi surfaces. For unit cell, we have clear Fermi surfaces. Here it's a little blurred, but we still have fairly some spectral wave even down to 1 unit cell. Now, if I look at compare thickness dependent Fermi edge here 4, 3, 2, 1, and you see that even though we still have metallic edge compared to 4 unit cell, the spectral wave is fairly suppressed. And immediate reaction is that maybe that's due to a disorder effect in ultra-thin film. So that's something we are going to check because this was this was a lot discussed in the past. So one possibility, one experiment we did was that we did alkali metal dosing. So basically, we put down alkali metal atoms on top of these films. And what this alkali metal does is that it donates electrons and in a cleaner way compared to chemical doping. Now, as soon as we dope a little bit of electron, what surprised us was that as soon as we dope potassium, the spectral wave suddenly grows back to like a fairly thick film of 40%. So here's a pristine without potassium. Here's a potassium doped film. The spectral wave grew as well as this quasi particle. Quasi particle grows. Now it's very clear. It's fairly weak here. And if we put down more electrons, actually this quasi-particle it grows, and this quasi-particle is extremely short. That means this disorder effect does not play a role here. So whatever this suppression is, that's not due to disorder effect. This is very intrinsic. That's the main message here. So our picture is that when we go to a very thin film, two-dimensional system, in 3-dimension, structure looks at 113, 3D system, we have a spectral wave near Fermi energy, and that splits into spin up and spin down, and resulting in ferromagnet. On the other hand, in the case of 2-dimension, like 1 unit cell structure lucernate, due to quantum confinement effect, dxy and dydx orbitals states have different density state. dxy has a band of singularity near Fermi energy here. Meanwhile, dydx, their density of state looks like this. Now let's focus on this xy. That can go into 2 directions. One, again, ferromagnet, spin up and spin down. That's how you lower your density of state at the Fermi level. Or another path is that this correlation-driven, basically you go into a Mott state. So what's happening basically for our case is that here there's a correlation-driven incoherence. So this is very close to Mott state, but with a very small Fermi edge. So not quite Mott state, but it's fairly close to Mott state. So we call that correlation-driven incoherency, and calculation shows that that's actually metal. Now, once we dope electrons, this density of state goes down, then we don't need this Mott transition to Mott transition because density of state is already low, and that's what we see Banach singularity moves away from Fermi level, and this quantum particle is restored. Now, once we find out that one unit cell film has at the verge of Mott state, Mott transition, we were thinking about whether we can control metal insulator transition in one unit cell. So let me show you earlier work on strontium leucinate 214. This is a single layer system, and as you replace part of strontium by calcium, it goes through a very interesting metal insulator transition. It turns out to be that as we replace strontium by calcium, first it rotates octahedron, then at a certain point it also induces octahedron tilting. And metal insulator transition, including orbital selective Mott transition, happens here. OSMT happens here, and true Mott transition happens around 0.2 or 0.15. So now single layer or one unit cell of strontium leucinate is very similar to this 214 system. So can we do similar thing using this one unit cell strontium leucinate film? So that was the question to us. So yes, the answer is yes. We can use different substrate. For example, we can use calcium titanate, strontium titanate, barium titanate. They all have, so this one has distortion. Meanwhile, even though this one doesn't have distortion, barium titanate has a slightly longer, larger lattice constant, and that can provide tensile strength. So if we grow strontium leucinate on top of these three substrates, this strontium leucinate layer follows the distortion in calcium titanate. So this one has both rotation and tilting. Meanwhile, if you grow single unit cell of strontium leucinate on strontium titanate substrate, we only have rotation. And on barium titanate, this rotation is minimal, very small. So this is basically what we do. This is very similar to what's happening here in this CSR system. So to check whether this strontium leucinate really follows the distortion that I described. So here we grew strontium leucinate on STO and strontium leucinate on CTO, and did lead measurements here. We found out that this strontium leucinate grown on STO has a root 2 by root 2 reconstruction. That means it's in tetragonal structure with rotation only. Meanwhile, if we grow strontium leucinate on CTO, we have 2 by 2 reconstruction. That means we have both rotation and tilting, and the unit cell is even smaller. So strontium leucinate one unit cell structure changes with this buffer layer, or CTO or STO this layer. And as we change number of thickness, layers, and substrate, the electron structure changes drastically. Let's look at here, for example, in one unit cell, film grown on barium titanate has very short quasi-particle. On CTO, you saw that before, it's insulator. On STO, it's almost insulator with a very small permeage here. As we grow, as we increase the number of layers, eventually they merge together and they all become ferromagnetic metals here. I show you map of Fermi surface maps. And how many minutes?
5 minutes. So maybe you can finish.
I need to pick one. Okay. Yeah. So, so we we have a coherent metal here in one unit cell strontium luthenate on PTO and insulator. So we could change all the way from insulator to correlated coherent metal of one unit cell strontium luthenate. You can also, what this tells us that by controlling this octahedron distortion, we can change from insulator to metal. So one can possibly imagine growing SRO on ferroelectric substrate, and maybe you can change the property from insulating to metal using this ferroelectric substrate. There's some suggestion from our work that that's possible by changing polarization of this ferroelectric substrate. We can also control metal insulator transition using strain, which changes the shape of octahedron. And indeed, we did that. Here, with the compressive strain, we have a fairly good ferromagnetic metal. Sorry, not ferromagnetic. Good metal, coherent metal. With the tensile strain, we have Mott insulating state here. So, if I were to summarize our work on strontium luthenate, I talked about nodal lines, metallic edges, and we control metallicity of this one unit strontium luthenate. We have other works on strontium iridate. We see signature of anti-ferromagnetic odor, even down to one unicell of strontium iridate. And since I'm not going to talk about, but we are also trying to grow single unicell of lanthanum strontium copper oxide, and we were able to measure band structures, even though at this moment we weren't able to make it superconducting. We have a single unicell copper oxide plate material with the electron structure. So let me summarize my presentation. I mostly talked about strontium luthenate work, nodal structures, metallicity in one unicell and their control. We could induce metal insulator transition by distortion and strain, and some short AF odor and electron structure of a single hypoxia plane. So this work is by no means the complete work, completed work. This is in progress. Basically, my presentation is more of a progress report. I haven't even, our work even hasn't started on this proximity effect. For example, what's going to happen when we grow this one unicell films on ferromagnet or interface with ferroelectric and control the electron structure. So many opportunities are ahead in these ultra-thin films of correlated materials. These work are published in these papers, and some are under review or interpretation. Finally, let me recognize our collaborators, many people. Here, ARPES, attentive groups, transport and magnetic property theory, and TM. So with that, let me thank you for your attention and for coming early in the morning.
Do you have any totally unexpected result? Because it's very difficult to do these experiments and very evolved, and you have beautiful control and everything, and you did nice numbers, so those of us who done it understand it. But was there any totally unexpected result? You were mentioning that you have a kind of edge in the single layer and stuff like that. Okay, but all of that was kind of at least part expected. But was there anything that would blow us out of this chair?
Okay. Yeah, good. First of all, this, well, I did talk about geomagnetism. That was also unexpected. Nodal structure. This is a totally unclear issue, and this is what's really new from that. Metallicity, well, it was one unit cell metal. Okay, that was an issue, and we solved it, so that's not, that was not clear before. We could do it. We can control MIT. That's fun, but as you say, that's expected. But that's not unexpected. What's probably unexpected was this. One unit cell structure irrigate. I did show you because of the time, but we have this double band, which is a clear sign of anti-ferromagnetism, and that's also inflamed. So that was that's in progress.
What is your success rate when you do, let's say, 100 samples or 1,000 samples? What is success rate in a way to get a picture or something for the publication?
Okay, so one unit cell, this is very reproducible. We found the recipe, and unless laser goes strange or some other environment changes, that's pretty much 100%. It's very reliable, actually. Quite surprising, but you're shaking hands, but I can tell you, it's quite reproducible.
I'm not arguing that, but you have to understand, even Mojich and myself done this for 40, 50 years, and our success rate is one sample in 10,000. I mean, when you get to nature, it's 1 in 10,000, and it's a 50th worse when it gets published. I mean, seriously. And we have books of samples that didn't work. So it's extremely difficult. I congratulate you if you can get it 100%. Frankly, I don't believe it, but I mean, I congratulate you and the whole team.
I think we can discuss maybe later. So, yeah.
Very nice. I was wondering,
Yeah.
maybe what you're looking at and demonstrating is that when you have one unit cell, you have an incredibly strong effect from the substrate.
Yeah.
I'll give you an example. We talk about layers, one unit cell layer that you put on strontium titanate versus calcium titanate.
Yeah.
But I guess you have taken into account that strontium. Have you taken into account that strontium titanate is a non-stoichiometric material and calcium titanate is stoichiometric? For example.
In terms of oxygen content you're talking about? Yeah. Okay, so here is one thing that I didn't talk about. Yes, that actually affects. Also, one thing that this is more detailed, so I didn't talk about that. But after we grow, after the growth, we have to anneal the sample because there's a little bit of carbon on top, and we need to burn off carbon by annealing oxygen. So that actually changes. So depending on this annealing condition, we can have different oxygen stoichiometry as you might expect. So we did that in different steps. There are different temperature steps, and there's an optimum temperature that's around 600 degrees C. So all these results are shown for 600 degree annealed sample. So I assume whatever there was some non-stoichiometry that's sort of like cured. So if we were to say, well, maybe that's not true, or maybe that's extreme effect, then maybe that's extreme effect. But anyway, there can be a little bit of a non-stoichiometry, but as you said, if there's a non-stoichiometry on our film, then we are not going to get, there was one question from the referee. First of all, strontium titanate, if there's a non-stoichiometry, you would expect some spectral rate and ferromagnet, but as you see, our ARPES data shows absolutely no spectral rate at 0 temperature. So we believe, well, I don't know up to what accuracy, but it's somewhat close to 0.
Okay, so
Discuss it, yeah, thank you.
yeah, I think we are running out of time. So one last short question in the middle. I saw, yeah.
Actually, I was going to ask, so in this superstructure where you're getting rid of charging, you put 4 layers, and then SPO and then prototypical. How do you know that this the states at the Fermi level are not coming from these 4 layers?
So the spectral ray, your question is whether the spectral ray can be from this layer, right? Yeah. Okay, so that's why we showed earlier.
Yeah, I think I know. So you have a spectrum without
Right.
Okay,
This one. Yeah. So there. I mean, 10 units is roughly thick as far as the tunneling goes. So this is basically the charging problem is solved through leakage current from tunneling.
And how do you do Hove experiments?
Excuse me?
Hove experiments, draft or
Hole
Hove
experiment. Yeah. So one is that we cannot do whole experiment. Whole experiment, we can do it down to 4 units. So show you again. Anything below 4 units, that becomes unreliable transport measure.
and you do that outside.
I think we should stop it here. Okay, so let's thank the speaker again.